Hello, welcome to week 4. This will be chapter 2, part 2. And what you're going to need for today is you're going to need your ion list, okay? This is one of the 2 things that needs to be printed, and so hopefully you have done that, or you have requested a copy from me. And the second thing that you're going to need for today is your periodic table. You actually won't need a calculator, which is handy, okay? Now, if, go ahead and go grab that if you need it. And I just realized I need to, okay. So let's go ahead and talk about nomenclature. All right. Moving things around my screen, always and forever, right? Okay. Okay, so what are we doing today? All right, so as I said, this is week 4. And we're doing chapter 2, part 2. And the big thing that we're doing during part 2 is section 2.8 in the textbook, if you have a textbook, and that is nomenclature. You might say, well, what is nomenclature? Nomenclature is basically naming compounds. So what we're doing is we're learning how to link the formula and the name. So we could say we're learning how to determine chemical formulas and their names. And the ones that we're going to be learning now are we're going to learn ionic compounds. We're going to learn covalent compounds. We're going to learn acids. And we're going to learn hydrates. If you go on and take organic chemistry, you'll learn a whole new set of nomenclature that's not really linked to what this is. Okay, so now we have the unpleasant part of the course. Everything must be determined using ion list and your periodic table, which is why you need them printed out. So especially as an online class, I had a lot of trouble last semester with students who basically ignored this rule, okay? So let me give you an example. If you are given a name and you can't figure out how to figure it out using these, and you look it up on the internet, there's a really good chance that you're going to get the formula in a form that isn't part of the way we're learning in this class. We're specifically learning a method that names ions and functional groups as units. We're not learning just a general how things are listed. It's not an organic chemistry thing. It's a very specific thing, and it's a very important thing because it's going to help us understand a lot of other things later, for example, structure. Okay, so if you look up a name on the internet, say you Google, what's the formula for, and then you put in the name and you get a formula, and it doesn't match this, that is considered cheating. The nature of chemistry is that sometimes I can prove this and sometimes I can't. Therefore, be warned, I will make the assumption that if you cheat once on an assignment, that you have cheated on the entire assignment. And any assignment with cheating or plagiarism, and this is in my plagiarism statement, any assignment with cheating equals 0 points. And you've probably learned by now that I let you redo recitations so that you can really learn from them. Any assignment or recitation where you earn 0 points because you have cheated on it, you will not be able to return in. The grade will be final, okay? So you're here to learn chemistry, learn chemistry. I'm very available to answer questions, okay? So do that instead of going to the internet. All right, so that was the unpleasant. Now, let's go ahead and go on and start learning some nomenclature. All right, so first of all, we have ionic compounds, and we're gonna start with that. Now, let's start simple, okay? And when I say start simple, what I want you to do is I want you to look at your ion list, and hopefully you can see the section in that little window that I'm looking at right here. Common monatomic cations and common monatomic anions. So we're just gonna start with that little piece, okay? And one example of that is, let's take a look at, I'm just gonna look at a couple of them here, and I see the potassium ion, and it is listed as K+. And then I see the chloride anion, and that's Cl-. Things are always listed cation, anion, always. Okay, they're not listed in any other way, always cation than anion. Okay, and remember that's positive, negative. Now, I like to say nature is neutral. Here we have one positive charge and here we have one negative charge. That means our potassium has lost 1 electron and our chlorine has gained 1 electron. So these balance out, 1 plus, 1 minus. They balance for 0. So that means that our potassium chloride is just KCl, 1 potassium, 1 chlorine. But it's not always going to be so neat and tidy. Let's take the potassium again. And let's look at potassium oxide. Well, the potassium we've already said is K+, and oxide is O2-. Now they don't balance. I need 2 positive charges to balance out 2 negative charges. So you could say, well, that means that I need 2 of these. 2 positive charges, 2 negative charges, and that means that my potassium oxide will be K2O. Okay, so potassium chloride is KCl. Potassium oxide is K2O. 2 potassiums and 1 O, 1 oxide. And notice that there is nothing in the name that has that 2 there. If you were to write dipotassium oxide, that would be incorrect. And it's very, very important when you're doing nomenclature, these have to be 100% correct to be correct. Because if you're a little bit wrong, then that's a completely different compound. And sometimes that can be really drastic. For example, if you're a little bit wrong, you might get a weak acid instead of a strong acid, or you might get a strong acid instead of a weak acid. If you're a little bit wrong, you might get a compound that will kill you instead of one that's safe. If you're a little bit wrong, you might get something that's extremely harmful to the environment instead of safer for the environment. So it's really, really important that these be 100% correct. And it's the one place where there won't be any partial credit. So you really do have to pay attention to what you're working with on these. Okay, let's look at another example. Let's look at calcium oxide. So I would go to my ion list and I would see that the calcium ion is Ca2+, and the oxide anion is O2-. Well, these are perfectly balanced. And because these are perfectly balanced, then I just have one of each, CaO. Now let's look at one that's going to be kind of weird. Let's look at calcium phosphide. The calcium ion is Ca2+, but the phosphide anion is P3-. Oh, so these don't match at all. We have 2+ and 3-. There's a couple different ways of doing this. One thing that you'll see is people, when they don't match like this, is that you just bring these down like that, and you bring the 3 down here and the 2 here, and then you just put them together. Ca3P2. Another way of looking at that is the idea that what you can have is you can say, well, okay, I have 3 of these, and that makes a 6+ charge. And I have 2 of these to make a 6- charge. And that's another way to think about balancing them out. You can use either method, okay? And again, it's that nature is neutral. But again, notice here that it's just calcium phosphide. It's not tricalcium diphosphide. There's nothing in the name for an ionic compound that matches the number of ions inside what we're working with. Okay, so now let's take a look at another case. And these are sometimes called type 2 cations. And on your ion list, they're down there. You can hopefully see them in the little window there. Common type 2 cations. These are usually made of transition metals and heavy metals. Transition and heavy metals have d orbitals available, easily available, that aren't necessarily available to other things. And because of that, you'll learn more about that in chapter 8 and chapter 7, but because of that, they can do some odd things. So an example of that is that iron, the symbol of which is Fe, can form 2 different ions. It can form iron 3, and that is Fe3+, and it can form iron 2, and that's Fe2+. And so you say, well, what am I doing here? These are Roman numerals, okay? And this is one of those cases, again, where you must include the Roman numeral for this to be correct, okay? Because iron 3 and iron 2 are really different ions, and they do different things. So you have to make sure that you include this in the name. Let's come over here and do a brief review of Roman numerals, okay? 1 is 1, 2, 3, 4. Sometimes you put the lines and sometimes you don't. I'm going to be kind of lazy here and not put the lines. 5. Okay. You won't get more than that in here. You can look it up if you want to know more of them. Okay. But remember what these mean. So let's take a look at what happens when we combine these. Let's look at the difference between iron 2 chloride and iron 3 chloride. Okay, well, iron 2 is Fe2+, and chloride, we saw from before, is Cl with a 1- charge on it. And iron 3, which we can see on our list, is Fe3+, and chloride is Cl with a 1- charge on it. So now when we look at this, we have 2 positive charges on our iron 2 and only 1 on our negative charge on our chloride. So we need 2 chlorides to balance out our 2 positive charges. So this becomes FeCl2. Iron 3 chloride is FeCl3 because we need 3 negatives to balance out those 3 positives. These are really different compounds, okay? And so when you are naming them, you really have to include the Roman numeral in order to match the compound, okay? All right, now let's take a look at some polyatomic anions. Okay, now our polyatomics are this long list on the side here. Okay, now there are 2 polyatomic cations. Only, excuse me, there's 2 that we'll be working with. One is, hang on. That's too hard to see. One is ammonium, and one is mercury 1. And just for comparison here, I'm going to put in mercury 2. That is not a polyatomic, but it's going to help us see the difference here. Now, the ammonium cation is NH4+. That means this NH4 acts as a complete unit, and the plus goes on the whole thing. Okay. Now, mercury 2 is Hg with a 2+ charge on it. It has 1 mercury that's lost 2 electrons. Mercury 1 is a little different. It's Hg2, 2+. And it's not Hg1+, it's 2 mercury atoms stuck together, behaving as a unit with a 2+ charge on them overall. Okay? Now let's take a look at what happens when we combine these with a simple anion. We'll just look at sulfide now for each one. And I know I've run out of room here, but we'll put this here anyway. Okay, so this is going to be ammonium sulfide, mercury 1 sulfide, and mercury 2 sulfide. Well, our sulfide is a 2- charge. And let's take a look at what happens here. Well, we have, and I like circling my charges. Ooh, look, I missed a minus. There we go. Okay, so let's take a look here. Here we have NH4+, and so we need 2 of these ammonium ions to balance out our 2 negative charge on the sulfide. And so what we have to do is we have to put the NH4 in parentheses so that we're saying that there are 2 complete ammonium ions that go with this 1 sulfide ion. Now here we have a 2+, 2-. So these are just going to balance out. And we get Hg2, S, and our mercury 2 sulfide, just for this comparison, will be HgS. Okay. Now let's take a look at some of the polyatomic anions. There are a lot of polyatomic anions, and again, they have to be in this form. Okay, it's really, really important. So let's take a look at a few of them. One of the things that I would very, very, very strongly recommend is that you spend some time with this, knowing where things are. You will need to know them very carefully for the entire rest of the semester. That'll be very important. Okay, so let's take a look at a few. Let's say that we're going to look for nitrite. hang on. I'm just gonna start again. Nitrite, nitrate, okay. Nitride, now I'm mixing a bunch of things up. Now I'll do sulfite and sulfate. This is my example of why it is so incredibly important to spell these correctly. And this is the one place during the semester where you absolutely have to have everything spelled perfectly. And that's because if we look here, we'll see that there's only one letter difference between nitrite and nitrate. There's only one letter difference between nitrite and nitride. Similarly, there's only one letter difference between sulfite and sulfate. However, nitrate and sulfate make very strong acids. They make nitric acid and sulfuric acid. And they're useful in certain places. Sulfite and nitrite make very weak acids, and they're very different. So it's really, really important that we understand where these differences are. Okay, so let's look at how to make these compounds. So nitrite is NO2 with a 1- charge on it. Nitrate is NO3 with a 1- charge on it, and these are all on your ion list here. Nitride is N3-. So make sure that you're really, really familiar with what's on here, okay, and that you know what you're looking for. Sulfite is SO3 with a 2- charge on it, and sulfate is SO4 with a 2- charge on it. Okay, that means 4 oxygens, 1 sulfur, overall 2- charge. Over here, we've got 3 oxygens, 1 nitrogen, overall 1- charge. Okay, so let's combine all of these with the same cation. Let's put all of them with aluminum. And aluminum is Al3+. Okay, so now I have 3+ and a 1-, which means I need 3 nitrites to balance out my aluminum. So I'll end up with Al, NO2, 3. Nitrate is also a 1- charge, and so I need 3 of them. And so aluminum nitrate will be Al, NO3, 3. Interesting thing, this is very soluble, this less so. So again, they can be very different, even though they don't look like they're really different. Now we have Al3+ and nitride. So aluminum nitride would just be AlN. Oh, wow. So now you can see a huge difference. Aluminum nitrite would be AlNO2, 3. Aluminum nitride, AlN. Okay, that's why spelling is so, so important here. All right, now let's look at aluminum sulfite. Now we have the 3+ versus the 2- charge. So this will be Al2, SO3, 3. You can see how these are more complicated. And now we have aluminum sulfate, the 3+ charge against the 2- charge will become Al2, SO4, 3. Okay. And again, these are quite different compounds. Now we're going to take a break from those ionic compounds, and we're going to name some covalent compounds. Covalent compounds are always between nonmetals, and they do not have ions, no ions. There is no give and take of electrons, they're sharing them. Okay, and because of that, we don't have the same simplicity of using an ion list to name them. And so we actually have to say in the name what the formula is going to be. And for that, we're going to need to use a list of prefixes. And these prefixes are in your slides, but I'm going to go ahead and put them here. First, we have mono, and that means one, but we don't use mono on the first element listed. We would only use it for other ones. And then we have di, 2, tri, 3, tetra, 4, penta, 5, hexa, 6, hepta, 7, octa, 8, nona, 9, and deca, 10. Okay, and so if you're just taking notes or something, I would have this in a set of notes just handy for recitations and tests and things like that going forward. So some examples of that now might be, let's say that we have carbon dioxide. You guys have all heard of carbon dioxide, right? So what we do here is we find this little prefix. That prefix means 2. And there's no prefix on the carbon, so it's just 1 carbon and 2 oxygens, O2. Simpler than the other one. Okay, let's take a look at the idea of carbon monoxide. Okay, and this is an example of where we're using that mono. We leave off the second O because it wouldn't be monooxide, it's just monoxide. And so that means 1 carbon, but only 1 oxygen. So there's carbon monoxide. Okay. Let's look at sulfur hexafluoride. And here's that prefix. So we have 1 sulfur and 6 fluorines, SF6. Okay. Let's look at dinitrogen tetroxide. So again, I look at this and I find my prefixes di and tetra, and di means 2 and tetra means 4. So now I have N2O4. And that's it for covalent compounds. As long as you remember the prefixes, they're pretty simple. The big thing to notice in this is here we've got carbon, oxygen, nitrogen, sulfur, fluorine. Covalent compounds will never have a metal. So it's good to say no ions, except that that's not a very good hint that, that you have a covalent compound. Because if you think about it, here we have fluoride, here we have oxide, so it kind of looks like we have ions. I mean, you could make ions with some of these. They'd all be negative, and so it wouldn't match, but you could, okay? But there's no metals in here, which means that there are no cations. So looking for the metals is a big thing. On the flip side, if you're working with ionic compounds, everything will have a metal or ammonium. That ammonium ion, the NH4+ that I had up there for cation, that would be the one time that you wouldn't have a metal in an ionic compound, but all of the rest of them have metal ions in them. And there is a periodic table in the slides that shows you metals versus non-metals. I don't know if you can see that from here, but it's right there, okay? And that will be a really good, good one to look at for that. All right, now let's take a look at the next one that we're going to talk about, and that is acids. Now, acids can be tricky. So what you need to do is you need to just have a really good flow chart telling you what to do when. You know you have an acid because it's going to have an H+ or a proton out front. So acids always start with hydrogen. Okay, and basically you make an acid by looking at your anions, and so it's always H plus and then an anion. So it's H plus and then an anion, and we have to balance those out. So let's take a look at a bunch of these actually. First of all, let's take a look at the first type, and those are called simple acids. And simple acids do not contain oxygen. And the way we name them is hydro, and then the anion root, ic acid. And this is a huge thing. So make sure that you make a note of it. Hydro does not mean hydrogen. Okay, people get really confused about that. They see this hydro and they think, oh, look, that hydro means the H. It doesn't. Hydro in this case means no oxygen. Okay, acid, the word acid, this is what tells you that you have H out front, but the hydro means no oxygen. So let's take a look at some possibilities for this. Here are some anions in here. We have the chloride anion, or we have the nitride anion. Oop. Here. Okay, chloride, nitride, and now there's one in the, actually there's two that are kind of hiding in the common polyatomics, and one of those is cyanide, Cn minus, okay. And in all of them, we need to combine them with H plus. So let's take a look at what that'll end up being. Okay, well, first of all, H plus and Cl minus, those just balance out. So we have HCl, and there's no oxygen in there, so we have hydro, and then the root, ic acid. So it'll be hydrochloric acid. Hydrochloric acid, the root here. Okay, now we have this next one, H plus and N3 minus. Okay, so for that one, we're going to need 3 protons to balance out the nitrogen. Okay, and here's the root. And so this one, no oxygen. So this would be hydronitric acid. Don't get that mixed up with nitric acid. Nitric acid and hydronitric acid, really, really, really different. And we'll do that on the next one. Okay, and then we have this last one. We have cyan in here, and that's just a 1-to-1 again. So we have HCN, okay, and no oxygen. So we have hydrocyanic acid. Okay, those are simple acids. Now let's take a look at oxyacids. Oxyacids are acids that contain oxygen. And we're going to name these based on what the anion name ends with. Okay, so let's go ahead and separate this into 2. And I like to tell it like a little rhyme. Ic to 8 and, sorry, let me erase that. It's 8 to ic and ite to us. So you won't notice the word hydro in this one. Okay, so let's take a look at what that means for some things. Remember, we're starting with H plus, and then let's say that we have NO3 minus, and this is nitrate. So these balance evenly, so we end up with HNO3, and you have that the root here, and it's 8 becomes ig. So this becomes nitric acid. Now remember we had that nitrous. We have NO2 minus, and this is nitrite. Again, these are super, super different acids, even though they look really similar. We have HNO2, but the ite becomes us, and so this becomes nitrous acid. Okay? We can work this part backwards too. Let's say that we have phosphoric acid. So I see that ick, and I know then that this must come from phosphate. So that's an interesting thing here. See how you include that OR in the name, but not in the ion? And so that's a good one to like think about, well, where this is coming from. Phosphate is PO4 3 minus. So I know that the formula for this, we need 3 protons to balance it out, becomes H3PO4. Okay. Let's say over here, let's work one backwards as well. That might be a little bit different. Let's look at sulfurous acid. Okay, I know that that OUS comes from ite, but it's not going to be sulfurite because we don't have that. It'll be sulfite. Okay, good example of what happens when you have one of these long, weird names. The sulfite ion is SO. Hang on, need to talk about the right one. All right, SO3 with a 2 minus charge. Okay, and so this becomes H2SO3 for sulfurous acid. Okay, one more. The last thing that we need to talk about are hydrates. Hydrates exist when you have an ionic compound, and ionic compounds are often just called salts. That just doesn't mean table salt. All ionic compounds are called salts. Okay, ionic compound plus water. And I drew a little dot there because that's how it's going to look in our formulas. So some compounds really like water, and they'll absorb water from the air, or you can make them specifically with water complexed on. So an example of that is copper sulfate pentahydrate. So you go through this whole thing, you say, okay, well, copper, I did not specify which copper. And that is important. Copper 2 sulfate pentahydrate, okay? So copper 2 is Cu 2 plus. And if you're wondering where I'm getting them, these are all on here, okay? Copper 2 and copper 1 are really different things. So it's important that that's specified, okay? Copper 2 sulfate, Cu 2 plus, SO4 2 minus. And then penta, remember, means 5, and hydrate means water. So now we put it together. Well, in this case, these balance perfectly. So we get CuSO4 and a dot, and then 5H2O. And this is the formula that goes with this name. Okay. All right. I look forward to seeing you in recitation.